Hi everyone, welcome to the general programming section. And to start off, we have Scott Haney telling us about writing maintainable Julia code.
All right, thank you. All right, so I'm here to talk to you about writing maintainable Julia code. One of the keys to this talk is that I'm very focused on you. I want you to leave this talk with something that you can take away and be a better coder with today. So I hope that whether you're an actual programmer or a practitioner that's just using Julia as a way to get answers to problems, that you'll be able to have some sort of takeaway that will help you. So I want to point your attention to this picture up here, right? This is something that's very well maintained. Right? And maintenance is a term in software that we run into. It's actually a term that falls under the category of software development or software design or architecture. And so this is actually architected and designed very well. And you can see from this that it's not simple, right? There's a lot of work, there's a lot of money, there's a lot of effort that goes into this. But nonetheless, if you go to this garden, you probably will go there and enjoy yourself. You'll probably go there and have a good time. You probably won't be thinking about all the different ways that they're not taking care of the roses correctly, or all the different ways that the water is dirty in the fountain, right? Because they've taken such good care of the details, you don't have to worry about it. The end purpose, you can just enjoy. So I want to contrast this with software development. So when's the last time that you had an enjoyable trip through someone else's code? When's the last time you had an enjoyable trip through your own code? Right? It's actually usually just the opposite. It's usually kind of a bad experience, right? And there's a lot of problems that we run into. Unlike the garden, there's a lot of problems that crop up about what actually is going on underneath. And so some of these problems, one of them is it's difficult to tell what's going on. So you look at this code and you think to yourself, okay, I'm having a problem with this part of it, but where is that, right? So it's hard to tell which portions of the code are responsible for that. The next thing, which is kind of obligatory for JuliaCon, is it doesn't run fast enough. And this is, an issue that will always be there. There's always going to be ways that you can improve it, but there is a good enough for your application that you need to pay attention to. Another issue is changes result in unexpected consequences. When's the last time that you went to the mechanic, got an oil change, and your windows wouldn't work anymore? Or the transmission blew, right? If that happened, you would probably find a different mechanic, right? But in software design, this is actually a common problem, where you change something that you think is isolated from other things, and all of a sudden unexpected stuff starts happening. And it makes you very afraid to use the software that you have. So two others, and these are very common, is adding a new feature would require a lot of changes. So one of the common terms in software architecture for this, for one way that this can happen, is something called shotgun surgery. So what that means is just like a shotgun. So a regular gun shoots out a single bullet, right? It's pinpointed. A shotgun shoots over a wide range and a lot of pellets. And so the issue is that what happens is there's some sort of concept in your code or some sort of issue in your code that's spread out through all kinds of different classes all over the code base. And what ends up happening is when you want to change one simple thing, you end up having to make changes all over the code. And similar to this is adding a new feature isn't possible without rewriting. This is a scary one. We run into it, right? I mean, how many libraries have you seen out there that might be on Windows, let's say, or on Linux, and people want it ported to the other operating system? And there's significant problems with this, right? Because they say, well, we would just have to rewrite the whole thing. We'll have to start all the way over. And that's kind of a killer, right? If you run into that problem, that pretty much means that either A, you're going to have to spend a lot of money redoing all this stuff, or else B, you're going to have to live with some pretty significantly reduced expectations. So let's kind of get to the high levels of why this occurs. It's only a 30-minute talk, so I can't get into all of it. So I'm going to stick to the high level that I think can benefit you. So let's talk about tools. So a hammer and a wrench are tools, right? And we know that they have certain uses and they're supposed to be used properly. And when they're not, things don't work out so well, right? So for instance, a hammer, right? It has certain requirements on it that you might not think about. It's a simple tool, but it does have requirements for its use. For instance, if you were to get your furniture and have to assemble it, which is pretty much what happens nowadays, and they actually put a place where you needed to nail in a nail that was too tight to swing the hammer, you'd be pretty upset, right? The reason is this tool, this hammer, requires that it has space to swing it. That's a requirement of the tool. And so we need to keep that in mind. The tools aren't perfect. They meet a purpose, and we need to keep that in mind. And problems that they have need to be mitigated rather than us coming up with 10, 20, 30, 40, 50 new tools. So even though this might seem like a simple example, I bet you have tools too. I bet no matter what field you're in, you have basic concepts that you use that are very common. And when you use these concepts, or when you encounter new problems, you try to mold those problems to the concepts you already have, right? You try to mitigate the limitations. So for instance, in electrical engineering, you have voltage equals current times resistance, right? That doesn't always work. It does in a lot of cases. It does under certain circumstances, and we try to restrict the problem of those circumstances under which it does work. Or inside of your computer with the static discipline of electrical engineering, as far as managing the signal errors. As far as systems biology from some of the talks earlier, we can't model the entire human body, right? So what we do is we come up with some sort of meaningful limitation that might not be perfect, but it's good enough. And then for those people that don't fit that model, we try to measure the side effects, and we see if there's something that can be mitigated, if they can be handled. So it begs the question, what is this tool actually designed to do for the computer? And this is very, very simple, but it reveals something important, and that's why I'd like to bring it up. So the computer, to us, ideally, should be like a black box, right? We want to ask it a question or tell it to do something, and then we want it to give an answer or do it, right? Ideally, that's what we would want. If you have a scientific problem, you want to just be able to say, this is my problem, put it into the computer, and the computer takes care of all of the stuff. You don't have to worry about threads, you don't have to worry about locks, caches, all these things that have been talked about a lot during this conference. Because that's actually a very scary and complicated world if you don't understand it. And even for people that do, it's quite complex. But this does reveal something very important. There's a what and a how. So this is kind of the key concept that I'd like to focus on for software design and architecture in this talk. So for the what versus how, there's something you want, and then there's some way that you're accomplishing what you want. And so for another example, there's the grocery store, right? You go to the grocery store, and on the left you have all of these cans, right? And there's a lot of details as to how those cans got there, right? There's manufacturing facilities that produce the cans, there's farmers that produce the crops, right? But at a high level, you really don't pay much attention to exactly the economics of how they paid the truckers to get it to the grocery store. You don't pay attention to how the steel manufacturers created the cans. You may pay attention to some of that at a high level. I mean, for instance, you might want a BPA-free can. You might really be concerned if the price goes way up, right? That can be something that comes to you, but you're really mostly focused on just a few core questions. Is it expired? You know, is it still good? Is it at a good price? Is it healthy? Is it organic? These kinds of things. And those how questions, even though they can kind of bleed into the what questions, you try to keep separated. So this is where we're going to get a little bit different. We're actually going to go through a real example of where and how we would do this. And so feel free to ask any questions. Again, this is meant to be helpful to you. Okay, so here's the demo. Can everyone read that in the back? No. Does anyone know if there's a way to make a Jupyter notebook full screen? Is there an option in here? Just have Command space? That'll work. Is that better? Okay, good. So we're going to go through a short demo here and try to work out what some of these issues are. So I'm going to put forward to you a number of things here kind of out of sequence because I'm trying to fit in things that are actually useful that I think you could benefit from. So the what and the how. So one of the important concepts in what is concepts, right? When you write code, you want that code to be in terms of things that you actually understand, things that other people might understand, right? If you're a physicist, you want the concepts of your physical problem to actually be findable in your code, right? When you're looking for something, you want to say, okay, there's a function that does this. I don't have to look all over the code base. I don't have to worry about it impacting all these other places. It's just in this one place and I can get to it. And so what we're going to do is we're going to focus on concepts. And the key to the programming toolbox is that for programming, you can start pretty much wherever you want, and you can bolt on all of these additional concepts over time. So you don't want to sit down and feel completely overwhelmed and think, oh my goodness, what am I going to do for threading? Which data structure am I going to use? What happens if things numerically overflow? You can get completely overwhelmed with all the possibilities. What if it isn't fast enough? That's an endless well, right? So what I'm going to put forward to you is that when you program, you can start with just a basic concept, and you can add the concepts that you need on. And so that does two things. It makes life a lot simpler for you, and it also means that you only start adding on the stuff you really need. Because a lot of times we get into this place where we're actually adding on a bunch of stuff that we think we might need that we really don't. So the background for the demo, I'm not going to spend a lot of time on kind of the math behind it, but it's something relatively simple I think a lot of people would have exposure to. It's iterative eigenvalue solver, so eigenvalue ax equals lambda x. And so the most basic of them all is the power method. So literally all you do is you take a vector x and you just keep multiplying it by the matrix. And what will end up happening is that if you have a vector that can be expressible in a basis of the eigenvectors and one eigenvalue that's much larger, then that eigenvalue is going to dominate, right? Because what will happen is as you keep multiplying by a, the powers of those eigenvalues are going to go up, and whoever's dominant is going to overrun everyone else. And so you're going to end up with that dominant eigenvector. Now, there are cases where that doesn't turn out correctly, but there are a lot where it does. So we're going to create an implementation for the power method. So this is the very first step that I would put forward to you to do when you start coding, is to think about the what. So when you think about something like the power method or any method, you want to sit down and think to yourself, what is it that I actually want it to do? And I know that seems like a basic question, but a lot of times we sit down and we code thinking we know what we want, just to find out as we're coding that all of a sudden this isn't going to work, right? And we have to go back, delete what we have, and start over. And so what I would recommend is that you start with focusing on what you want at a high level and create an outline. Because if you're able to create an outline, then you have some kind of reasonability that this is going to work. So for the power method, it's pretty simple, right? All you're going to do is, in some sort of a loop, you're going to keep multiplying by a. At some point, you're going to want to stop, right? You don't want this thing to run forever. And you're also going to want to worry about numeric overflows, right? Because if this thing keeps going and going, you're raising numbers higher and higher. The machine can't handle, above a certain precision, and it's going to overflow and give you wrong results. So here's the outline I created for this. So power method, and there's a few things that are overlooked, so I'm not paying any attention to the type system as far as figuring out a general way to handle types of matrices. So we're just going to assume we're dealing with float 64 everywhere. And then I've created an interface for the stopping criteria, right? And this interface is going to take this should stop method. And the should stop method is going to determine if it should stop, right? So all we're doing in this method is we're looping. We're seeing if we should stop based on the stopping criteria that we pass in. And then we're going to use a normalized step. That normalized step is going to make sure that these numbers don't grow out of control and that the whole thing doesn't crash on you. And then once we've decided to stop, we're going to return the vector that we have. Okay, so the next problem is that outline is nice, but it doesn't actually do what we want it to do, right? It's not going to solve anything. Well, that's where we bolt on the next idea. So now that we have the outline, let's actually get something working. So one of the things, if you remember numerical linear algebra, is the Raleigh Quotient. The Raleigh Quotient is basically a least squares approximation to the vector that you have to tell how close it might be to an actual eigenvector. And so I'm just going to slap that in there. and I'm going to put it into the architecture that's already there, right? So what I'm doing is I'm creating this new residual class, and this is a stopping criteria, and it contains the information that I want to specify, so the configuration for how and when I want it to stop, which is going to be when it's below a certain residual, so when it's close enough to an actual eigenvector. And then I'm going to create a new instance of the should stop method, right? And in this guy, all I'm going to do is calculate the Raleigh quotient, see if it's close enough. And then notice what I do down here. All I need to do is I just need to throw that into the power method. What I did not do is change the power method. The algorithm did not change, right? So if you remember back to design principles, there's this term called solid, right? And the O in solid was for open closed. If you remember, that was open for modification, or sorry, open for extension, closed for modification, right? And this is that principle. So I haven't actually needed to modify the actual algorithm. The algorithm has provided me arguments that I can override, and by doing that, I can extend it without actually needing to change the actual algorithm itself. So I'm going to try to kind of go quickly through this. So the next requirement. So let's go to another requirement, and this is a little bit contrived, obviously, because I'm doing a speech, but you could really go about this looking at steps in different orders, different steps. It really doesn't matter. That's the way that ideally this tool of the computer should work, is that once you put things into concepts, all you need to do is just keep bolting the concepts on no matter where you are. So let's come here. So for step 3, one of the things is I don't want it to run forever, right? It's possible I could just get a really bad value, right? And it's possible that value may not converge very quickly. It could run 10 million times, or it could run indefinitely if there's actually no eigenvector. So I want to have some kind of a constraint where it says, okay, things aren't working out well, let's stop this train. So what I'm going to do is I'm going to add a new stopping criteria, which is called exactly n iterations, and it's going to stop whenever the iteration count hits a certain value, right? And the issue is that I want to compose this with the other criteria that I have, right? Because these are meant to work together. So I'm using the residual. If the residual doesn't work out, I'm having this kind of backup plan. And so to represent that, I have a composite stopping criteria. And that guy has a should stop, and all he does is he looks through all of the criteria that he has and determines if any of them say it should stop, and he stops. So that way, if the residual is still not at a place where it should stop by the time the iteration count is hit, the iteration count will stop it. So design-wise, this is okay, but there is one issue that I have a comment about here, and that's this number of iterations, right? You'll notice that when I did my outline, I didn't, in the should stop method, put any kind of a reference to how many iterations there were, right? I didn't do that. That was a mistake I made, but it's okay to make mistakes, and that's one of the things that you need to keep in mind, is if you're missing a concept, and so this concept is that when I need to stop, I may need to take into account how many iterations there are. So what I want to do is I want to say, okay, well, what would really make my life easy? What do I want? So the easiest thing, the most straightforward thing that you would want is you would want this method to take num iterations. Right? Because if that method took num iterations, this whole thing would be wonderful, right? Life would be great. So let's do that. So now that we've done that, let's go up and make the changes backwards that we need to. So all should stop methods are going to have to take it. And then the power method is actually going to have to calculate this, right? So this is actually pretty simple, right? Just num iterations is 0, and then each time through increment. And now we're going to pass it in here. And then there should be one more for the composite stopping criteria. So you see there, I kind of had to go back and change some things because there was a concept I was missing. That's okay. That's okay. You just want to keep it to a place that's easy to manage and easy for you to understand. So now that we have that, we've created our function. And so now let's go on to a new step. So let's deal with an actual use case here. So this is what I would consider an unexpected use case. So the unexpected use case is, and this is a real life use case, at least the case itself, is the Google matrix. So the Google matrix is used for internet searches, right? And so that's a gigantic matrix that they use. And yeah.
In the first power method thing, there was a typo on iterations.
Oh, okay. Thank you. Okay. So back to the matrix. So the issue is with this matrix, they need to calculate the dominant eigenvector, which the power method is really good at that. And going back to this whole idea of tools, right? When we have problems in our fields, we try to match that problem to the tool that we have, right? And so the power method is one of the simplest eigenvector solvers there is. And so Google's kind of designed things so that they can use this very simple tool intentionally. And so what they say is they say that they have their matrix defined in such a way that you're not going to have to really worry about too many iterations of this method. You're not going to have to worry about it going crazy. You're not going to have to worry about it not converging. You know, in some number of iterations, it's going to come to an end, right? Because they want your search to actually complete and complete quickly. And so what I'm going to say here for the requirement is that we know what n is. So let's say that we've designed our matrix in such a way that we know that if we do 5 iterations of the power method, that everything is going to turn out wonderful. So this is kind of an interesting one to do, right? Because it's actually pretty easy. What we did before, when we did the making sure that the thing doesn't run away, is we added this exactly n iterations method. But that's exactly what we want here, right? We want to stop at exactly n iterations. And so the thing about this is that since I've broken up my previous code into concepts, you'll see that those concepts kind of get reused and I get something for free here, right? Because I've broken it up into concepts that make sense for the domain, that make sense to me, I have the ability to reuse this concept. And in fact, I have to do very little code for this, right? It's just using what I already have. Okay, so let's go to another one. So in this next step, we're going to actually add a completely new idea. So in our original code, we had the normalize method to make sure that the numbers weren't running away from us, right? But now, let's say that this Google matrix, you know, Google spends a lot of their time and computing resources on these searches, right? So maybe they don't want to have to normalize that vector. Maybe they've designed their matrix in such a way that you don't have to worry about that, right? It's a limited number of iterations. And for every Google search, if you avoid 5 normalized methods, that could add up to a lot of money. So let's say that we want to swap that out. So the issue is that we have another concept here, right? And that concept here is how we handle the overflows. And so for this one, rather than creating a type, I'm just going to pass in a function that matches a certain signature. And so that signature is going to basically be my interface into this function. So what I have is this overflow handler, and these are the 2 implementations of it. The normalize strategy, which is what I had before, and then the do nothing strategy, which is what they want. So I've just copy pasted the code here for simplicity. And you'll see that when I actually want to run it, all I'll do is I'll just switch out the different strategies. So if I want to normalize it, I'll use the normalize strategy. If I don't want to, then I'll use the do nothing strategy. Okay, so kind of trying to wrap up here, one last concept that I want to really fit in is this issue kind of going back to the what versus how. So in software architecture, when you think of what versus how, there's a term that's really important there. It's called the composition root, right? And the composition root usually consists of a lot of factories. And in this case, this is this is an example that I'm giving of one of the factories that's very important. It's called an abstract factory. An abstract factory, unlike a regular factory, doesn't just create an object, right? A factory just creates something. An abstract factory knows how to create groups of things. So if you have multiple things that need to go into a method, like Power Method has two things now, right? It has something to handle the overflow, and it has something to handle when it needs to stop. But some of these might not go together, right? The custom overflow strategy that we created for Google, if that goes into the default method for someone else, it could cause problems, right? Whereas if the default method goes into the Google method, it could cost them a lot of money. So what we want to do is we want to create methods where we can specify more specifically what we want, and then it'll compose these objects together for us. And once we have these objects, we just throw them into the Power method. So now at the top level, all we're doing is we're saying we have two different strategies. We have this Google-specific strategy, and we have this default strategy. And for both of them, they're just going to return these two dependencies that the Power method needs. And then I'm just going to throw them in there. And so this whole top above the Power method is kind of like our what, and it goes along the lines of this idea of a composition root, where you specify what you want, and then this is the code that's responsible for putting together all the pieces that create what goes into the method that determines the how. And underneath here, the Power method, this is where you have all of those scary things like, threads or, locks, all these very specific things. Whereas the what is very unlikely to change, right? The fact that you want to solve for eigenvectors, that you want to handle overflow, that you want the thing to stop. I mean, when is the next time you're going to want the algorithm to run in an infinite loop? Probably never, right? So there's a huge difference between these two pieces of code. And in general, when you're coding, you'll find that a lot. And so by separating this what, I've created something that if I come back to this 6 months from now, it's probably going to be the same. So if I have an understanding of that, I'll still have an understanding of that 6 months down the road. And then the how can change a lot of times. But it shouldn't affect the what too much. So wrap up and conclusions. So you want to separate the what from the how. So as much as you can, you want to represent things in terms of what you understand, what people in your field would understand, so that this is easy to use, easy to find stuff. Kind of like a balanced binary search tree, right? When you're in a balanced binary search tree, if you know the first step, you've eliminated half the tree, right? If in your code you have it broken up into concepts at a higher level, then if you know what concept you're in order to make the change that you want, you've kind of eliminated a lot of code that you have to look at or understand. And the other thing too is if you're worried about performance for this, right, because we're adding abstractions which can have performance overhead, it's the top level that's the most important, right? So at the very highest levels, you're usually not running this code as much, and so performance doesn't usually come back to bite you. If you run this at a lower level, like for instance, instead of threads, you have tasks, right, and you're running lots and lots of tasks, right? That's a new abstraction we've been introduced to here. Then that can add a lot of overhead. But you want to keep it at a high level because that's really where it benefits you anyway. The further down you go, just like the further down the binary search tree you go, the less and less you're excluding. And so the how you want to keep separate, and that can change a lot, and so that way you can kind of separate that out into something that you can ask someone easily to figure out. You can say, hey, I've separated my code out, and I know you're an expert in this, so can you go and implement the Power method? And they wouldn't have to understand all this other stuff, or if they needed to implement a custom stopping criteria, they wouldn't even have to understand the actual method, right? All they would have to understand is stopping criteria. So again, in conclusion, we want to separate the what from the how, and that'll help us to better understand what's going on and also to make life easier for us and for people who are reading our code. The how can change a lot, right? And that makes it difficult, right? There's a lot of details in here that can change a lot, so we want to separate that out so these two things aren't intertwined. And now, building software iteratively, this is the way that's best for the tool that we have. It makes it simple to make sure that we're not overthinking things. It makes it simple to make sure that we're not putting in a lot of things that we don't really need. And then we want to keep our concepts small, right? So when I use these concepts, right, like the stopping criteria, you notice how we were able to reuse the criteria that stopped at exactly n. That was because we had a small concept that we could easily reuse somewhere else. So you want to keep your concepts tight. That way they're easier to reuse in other places. And so I hope this benefits you, and I hope you go away with a better idea of how to write your code maintainably.